Hello all. Thanks for having me today. It's good to be here. This is a great group. I attended my first meeting last year, and it was really exciting. It's good to be in a room full of folks that you have a shared passion with. So yeah, thanks again. So my name is Ben Rao. I work for the U.S. Forest Service Northern Research Station. I'm based out of Parsons, West Virginia, and today I just wanted to talk with you a little bit about measuring and modeling soil moisture in complex terrain for forest management. We've covered a great deal of the things that I was going to talk about today. You know, when you give a talk at 3 o'clock in the afternoon, some of your thunder gets stolen inevitably, but that's okay. You know, everyone did a fantastic job today. And so maybe I can just kind of put some of this in the context of forested ecosystems rather than, you know, talk about, you know, data and results and things like that. And so, you know, a lot of what I do want to talk today is based out of the Furno Experimental Forest over in Parsons. And we're kind of launching a new effort there, a soil moisture effort there, in partnership with a lot of different folks. So I've been working with many contributors. This is certainly something I have that I could not do alone. I'm a man of limited skill. And so, you know, it's good to have surround yourself with people who know more about different things than you do. So, you know, I want to thank all these people on the efforts that they've put into making this thing possible. There are some unique challenges to understanding soil moisture in complex terrain. You know, a lot of forested ecosystems are on lands that are basically not suited for agricultural production, and they're not suited for urban development. They tend to have very steep slopes. Those slopes have multiple aspects. Some of the soils are extremely shallow, depth to bedrock, and many of them have many coarse fragments. So channery soils and rocky soils. And those characteristics have unique influence on soil moisture. And, you know, as we know, and as Claudia has mentioned and other folks has mentioned, you know, soil moisture is a critical driver of hydrological and ecological processes, you know, runoff and erosion, landslide hazards, primary production, carbon storage and greenhouse gas emissions, think nitrous oxide emissions, denitrification, methane emissions. And also, you know, very important to us is the probability of wildland fire, the determination of its size and its severity through the feedbacks with live and dead fuel moisture. So understanding this continuum between soil moisture and live fuel moisture, plant fuel moisture is really important. And so our managers, you know, through talking with our managers out there on the ground, folks like Claudia and her counterparts, you know, they have some real serious concerns that, you know, obviously we try to provide answers for them as a R&D organization. And sometimes we don't have all those answers, but we try. And so, you know, as she kind of alluded to, there's, you know, forest harvest operations and planning operations, you know, is really important, just as any farmer or agricultural, you know, manager would be interested in, you know, is my field too wet to plant? Is my field too wet to harvest? You know, we're also interested in making sure we don't do irreparable damage to soils through mechanical and machine operations. Drought stress is also very important, you know, understanding, you know, when our trees are drought stressed, you know, when these systems are drought stressed, because those things can lead to insect and disease outbreaks, which can be have a tremendous economic and ecological damage in forested ecosystems. And also, you know, these measurements can help us drive prescribed fire and wildland fire decisions. You know, we saw, was it last year, 2 years ago, you know, a prescribed burn gone awry, which caused a tremendous amount of damage. You know, and sometimes when you see maybe the atmospheric conditions are right, say the wind speed's right, the air temperature's right, the relative humidity is right to light off a pea burn, you know, it may be that your fuel moisture is very low. And so perhaps, you know, through better soil moisture measurements, we can get better handle on some of those things. And also just thinking about, you know, and the other thing I was thinking about too with wildland fire certainly is then, you know, correlations, and I talked to Jonathan about this a little bit, is, you know, correlations between soil moisture anomalies and, you know, probabilities of ignition, but also rates of spread and ultimately fire size. You know, we're in an era now where we see fires that do not behave like they used to. You know, we're essentially, the fuels are extremely combustible. They burn like we've never seen before. We're getting fires that are way larger than we've ever seen before. You know, essentially what we're talking about is something that is unsuppressible. You know, it's behaving in a way that you can't even get near it, and it doesn't matter what you throw at it, it's not going to go out. So, you know, so understanding like what drives that kind of fire behavior is really important. And then long-term planning for climate change. So certainly we think about oh, as the climate changes, particularly in arid environments, as it gets hotter or drier, do we have certain species on the landscape that are going to be pushed off of the landscape? Are our ecotones going to shift? Or are we going to see northward migration? How do tree species respond to these changes in climate? And so understanding something about soil moisture can help us with that. Are there concavities on the landscape, or converging zones where you might have refugia for certain species, things of that nature. Soil moisture certainly drives the distribution of plant species on the landscape. And so you've probably seen a slide similar to this today, thanks to Matt. So currently, for our forest managers, the desired high resolution spatial and temporal soil moisture data sets basically are not widely available for forest managers. Because the terrain is so complex and dissected, a 1 kilometer grid cell doesn't tell you much about local soil moisture, on a valley bottom or a hill slope or something like that. There are land surface model products, but those are pretty intense, to run, and maybe not practical, and also probably not at the scale that we need for management decisions. And typically, our existing monitoring networks are macro in scale, unevenly distributed, and generally focused on agricultural landscapes, right? A lot of our networks are, mesonets, widely dispersed, tens of 30s or of kilometers apart. And also, there's certain areas of the country that aren't even well represented, and particularly forested landscapes. A lot of these sites are on nice grassy spots representative of agriculture or grazing lands or something like that. Certainly not under a tree canopy. And maybe the snow-tail sites are in mountainous and rugged terrain, but those two would not typically be under canopy cover. And so we're aiming to try to improve that or build upon this. And so this is the Furno Experimental Forest is located in Parsons, West Virginia. So the U.S. Forest Service operates several experimental forests. These are areas set aside within the national forest where we conduct experimental manipulations that help guide our management. And so the Furno is also, in addition to being an experimental forest, it's an experimental watershed. So you might be familiar with things like the Coweta Hydrologic Lab or the Hubbard Brook Experimental Forest, or if you're from the Western US, things like the Kings River Experimental Forest or Fraser Experimental Forest. Those are all part of our experimental watershed networks. And so at Furno, we have 10 watersheds. Essentially, these are relatively high elevation catchments. So these are headwater catchments. These are not big drainages. And we've been basically gauging, these experiments were originally set up in the 1950s to look at the impacts of forest harvests on water yields. And since then, we've kind of adapted them for several other purposes. Oh, look at that, nice. So, I mean, this is pretty typical of what goes on at the Furno. We're gauging our streams or headwater catchments with 120-degree V-notch weirs. And we've got essentially, an array of meteorological instruments out there. We've been gauging air temperature and stream flow and precipitation since 1951 out there. So over 70 years of long-term meteorological records, stream flow records. Starting in the 80s after the Clean Water Act was passed, we started doing precipitation chemistry and stream chemistry. And so we've also operate an NADP site out there, after the implementation of the Clean Air Act. And that might actually be, if that is not the first NADP station, it is one of the first NADP stations ever established. So these sites, this site in particular, and some of our others are just really good long-term opportunities for studying climate change and management. And so one of the things that we're trying to do is set up a soil moisture network that essentially will help us better understand how water is redistributed vertically and laterally in complex terrain. So not necessarily a mesonet, but more like a micronet. So essentially trying to understand, how hill slope position, slope, and aspect influence soil water availability. So looking at ridge tops and mid slope positions and valley bottom positions and, north, south, and east aspects. And when I first started thinking about this about 2 or 3 years ago, I kind of reached out to Mike, and we started thinking about how we might set this up. And I started with one little watershed, with my idea. And then he said, well, we should expand this to think about, remote sensing too, because this is possibly an area that we could use to test remote sensing products. So we kind of expanded the network, at least the plan for the network. This doesn't exist yet, to cover kind of a SMAP pixel, but then also kind of laid the NISAR grid over it and thought about, how we would distribute sites, when that thing ever launches, if we could ever. And I actually did submit an early adopter proposal to NASA, and they said, sure, we'd love to have you. So that's great. And so, we're partnered with this actually with the NRCS. I was looking for funding for how to get this done. And NRCS stepped in, and as part of their dynamic soil survey and their dynamic soil properties initiative, which is really cool, and I hope you all get a chance to learn more about, they were able to at least fund 15 stations out there. And the first 15 stations that we implemented, we put in the ground last year, and those are those stations in red. And we're hoping that basically that these things will help us to parameterize hydrologic models, hydroecological models, and remote sensing data products, so that we can kind of deliver this information to our constituents. And I won't bore you with a ton of data because it's not great data yet anyway. So we put the stations in September. Batteries died in May. So we're learning how to operate this network. Essentially, at this point in time, we're working out the kinks. And we put sensors in at these are Tyros 12 sensors on top there, the volumetric water content sensors at 10, duplicates at 50 centimeters, and then pretty close to the bedrock interface in saprolite, 80 to 100 centimeters, depending on how far we could get. Every single one of these pits that we dug was done in conjunction with NRCS. They came out and did a complete profile description. We took samples of bulk density, particle size analysis, organic matter content, yada, yada, yada. What you're seeing on the bottom there, so in addition to volumetric water content, we were also interested in matrix potential. So that's a Tyros 21. And I'm not sure how I feel about this yet, because none of the data looks super good. But this is one of the things that I think is neat to point out, is that, in forested ecosystems with a lot of coarse fragments, it's just really difficult to get good soil to sensor contact, with some of these instruments. And so the quality of the data, might not be what you're expecting. So yet another challenge of dealing with forested ecosystems. So this is from a hilltop position. You can see that, there's kind of spread in the volumetric soil water contents, and then this is a valley bottom position. And you can see that spread is kind of not as great. So, hill slope position does actually, play a pretty important role here in what we're seeing in moisture distribution across the landscape. And again, you can see that logger, and this is all kind of during the wet up, you get a recharge period, and then, we're basically looking at the non-growing season here. So nothing too terribly exciting. One of the questions we had is like, how do we deal with this data? Like, what do you do with all this time series data? How do you analyze it? How do you tell what slopes are different? How do we kind of analyze this and determine, how these landscape positions differ? And this is some work that I'm doing with some colleagues from the University of Georgia, and also from the ARS lab in Davis, California, and looking at essentially looking at the soil moisture recession curves. So that the first part of the recession curve is basically drainage due to gravity, between saturation and field capacity. And the second part of the recession curve is basically due to ET. It's from field capacity to wilting point. And so a gentleman named Member Mellis, super bright engineer, came up with a way to extract all these slopes from the time series, looking at what he calls slope 1 and slope 2 to characterize these recession curves. And then applies a couple different metrics to them. Basically a flashiness index, like you would apply to stream flow, looking at, basically how flashy the system is, and then the total cumulative slope reversals. So, how many of these spikes do you get, essentially throughout the growing season? That helps you tell you something about soil physical characteristics, the impacts of particle size, texture, bulk density, but also slope position. And also then, even the climate and vegetation influence. So, this is a way that we might be able to compare, time series across different landscapes and different climates and different vegetation types. One of the other things we're working on is process-based modeling, and trying to incorporate multiple horizon modeling into process-based models. So this is a rhesus model, which is an eco-hydrological model. And so, models like this can help us kind of, look at the impacts of climate change or forest management on tree species distribution, moisture availability, stream flow, things like that. And so, typically the underlying model here is typically either a top model or DHSBM, and it's kind of treats the soil as one bulk layer, giant layer. And what we're trying to introduce here with a colleague of mine, Antoine Randolph, is actually trying to, model individual soil horizons and put that into the model. So, different tree species have different rooting depths, and so that drives species competition on the landscape, depending on, where your trees have their roots and what the water content is in different soil horizons. So, a model like this can be really helpful for us. And of course, the remote sensing angle. If we get a chance, it'd be really nice to fly UAS mounted radiometer over this site, or perhaps even use a tower-based radiometer to actually kind of look at temporal change in the moisture signal over time instead of just like one time. So lots of things to think about. Yeah. And it looks like Mike's there, and I'll give you an opportunity to move on to the next one. But thank you all very much. I appreciate it. If anyone has any questions, I don't know if you have a time or not.
All right, thank you, Benjamin. You have a question? You have one question for Ben? Questions?
Hey, Ben, thank you for your talk.
Yeah, thanks.
So what did you use for the slope position map? Was that something that somebody on your forest created, or is there an algorithm or?
I mean, if you're an ArcGIS user,
Yeah,
if you go into
I'll talk to you about it
the
later.
raster tools, you can develop a slope position raster
Right.
essentially based on any DEM.
Gotcha. All right. Thank you.